Welcome to this coding problem walkthrough. Today, we'll be diving into problem number 1231, divide chocolate. This intriguing problem challenges us to divide a chocolate bar in a way that maximizes the minimum sweetness of the pieces. It requires a blend of problem-solving skills and algorithmic thinking. Let's explore the problem and strategies to solve it. Imagine you have a chocolate bar made up of n chunks, where each chunk has a specific sweetness level represented by an array called sweetness. Your goal is to share this chocolate with k friends, but in a way that ensures fairness. The chocolate will be divided into exactly k plus 1 pieces, meaning you and your friends will each get one piece. To make it fair, you want to maximize the minimum sweetness of any piece that you give away. The problem asks you to write a function that calculates the largest possible value for this minimum sweetness. The input includes the sweetness array, where each element specifies the sweetness of a chunk, and an integer k, representing the number of friends. The output should be a single integer that represents the maximum possible minimum sweetness achievable under these conditions. Let's look at an example to better understand the problem. Suppose the sweetness array is 1, 2, 3, 4, 5, 6, 7, 8, 9, and k equals 5, meaning you want to share the chocolate with 5 friends. In this case, the chocolate must be divided into 6 pieces in total. One way to split the chocolate is into pieces with sweetness values of 1, 2, 3, 4, 5, 6, 7, 8, and 9. The minimum sweetness among these pieces is 6, and since we're trying to maximize this minimum value, 6 is the answer. This demonstrates how the division aims to be as fair as possible while maximizing the smallest sweetness value across all pieces. Here's another example to consider. If the sweetness array is 5, 6, 7, 8, 9, 1, 2, 3, 4, and k equals 8, the chocolate must be divided into 9 pieces. In this case, each piece will contain exactly one chunk of chocolate, such as 5, 6, 7, 8, 9, 1, 2, 3, and 4. The minimum sweetness among these pieces is 1, which is the answer in this scenario. This happens because with so many friends, each person receives only one chunk, so the minimum sweetness is determined by the smallest sweetness value in the array. Now, consider one more example where the sweetness array is 1, 2, 2, 1, 2, 2, 1, 2, 2, and k equals 2, meaning the chocolate must be divided into 3 pieces. One way to split the chocolate is into 3 chunks, 1, 2, 2, 1, 2, 2, and 1, 2, 2. The minimum sweetness of these pieces is 5, which is the maximum possible minimum sweetness that can be achieved. The problem also specifies constraints, such as the array size being up to 10,000 and individual sweetness values being as large as 100,000. For edge cases, if k equals the length of the array minus 1, each person gets exactly one chunk, and the minimum sweetness will be the smallest chunk. If all sweetness values are the same, the result will simply be that value. Finally, for large arrays, an efficient approach like binary search is necessary to solve the problem within a reasonable time. To start, let's discuss the brute force approach. The main idea here is to try all possible ways to divide the chocolate into k plus 1 pieces, calculate the minimum sweetness for each division, and then maximize this minimum sweetness across all valid splits. This involves generating all combinations of k cut points to divide the sweetness array into k plus 1 subarrays. For each division, we compute the minimum sweetness of the resulting pieces, tracking the highest minimum sweetness overall. While this guarantees correctness, the computational cost is extremely high. Generating combinations of k-cuts among n1 positions grows exponentially, with a time complexity of O, C, n1, k. On top of that, calculating the minimum sweetness for each split adds an additional O, n, making the overall complexity O, C, n1, k, asterisk n. As you can imagine, this becomes infeasible for larger inputs. The trade-off is that while this approach is conceptually straightforward, it's computationally impractical for scenarios with large n or k. Now let's explore the optimized approach, which uses binary search on sweetness to significantly improve efficiency. The intuition here is that instead of trying every possible split, we use binary search to directly find the maximum possible minimum sweetness. This is based on the key observation that if it's possible to divide the chocolate into k plus 1 pieces with a minimum sweetness of x, then it's also possible for all values less than x. To implement this, we check the feasibility of a given value x by greedily dividing the chocolate into pieces, ensuring that each piece has a total sweetness of at least x. If we can create at least k plus 1 pieces, then x is valid, otherwise, it isn't. To perform the binary search, we set bounds. The minimum sweetness starts at 1, while the maximum is the total sum of the sweetness values. For each midpoint value x, we check feasibility and adjust the search range accordingly. Once the range narrows down, the largest valid value of x is returned as the result. This method efficiently hones in on the optimal minimum sweetness without needing to evaluate every possible split. The binary search approach is not only efficient but also scales well with larger inputs. Binary search itself takes O log s, where s is the sum of the sweetness array. The feasibility check, which involves iterating through the array to compute the sweetness of each piece, takes O n. Combining these two, the overall time complexity of the approach is O n asterisk log s. This is a dramatic improvement over the exponential complexity of the brute force method. The trade-off is that binary search requires a careful implementation of the feasibility check, but this extra effort is rewarded with significant performance gains. Ultimately, the chosen strategy is binary search on sweetness. It leverages the monotonic property of the problem, which states that if a minimum sweetness value x is feasible, all values less than x are also feasible. This property allows us to narrow the search space efficiently. The greedy feasibility check ensures correctness while maximizing the minimum sweetness. For competitive programming or real-world applications, this optimized approach is the clear winner due to its balance of speed, scalability, and reliability. The problem we are tackling involves dividing a chocolate bar, represented by an array of integers called sweetness, into k plus 1 pieces. Our objective is to maximize the smallest sweetness value among these pieces. In simpler terms, we want to ensure that the least sweet piece of chocolate is as sweet as possible, given the constraints. To approach this, a brute force method begins with understanding the problem. The array elements correspond to sweetness values of consecutive chocolate pieces, and by making k cuts, we divide this array into k plus 1 subarrays. The challenge is to find an arrangement of cuts that yields the highest possible minimum sweetness value. To achieve this, we start by generating all potential ways to make k cuts, which involves selecting combinations of indices in the array. This step can be implemented either through recursion or by directly using helper functions like itertools.combinations in Python. Once we have all possible combinations of cut points, the next step is to evaluate each split. For each set of k cuts, we divide the array into k plus 1 subarrays, calculate the total sweetness of each subarray by summing its elements, and identify the smallest sweetness value among these subarrays. This smallest value is what we aim to maximize. To do so, we track the maximum of these minimum sweetness values across all valid splits. Finally, after analyzing all potential splits, the result we return is the highest minimum sweetness value found. While this approach is straightforward, it involves significant computation since we must evaluate every possible way to divide the chocolate. The brute force method, while conceptually simple, suffers from exponential time complexity. Generating all combinations of k cut points results in a combinatorial explosion, with a time complexity of O n to the power of k. Additionally, for every combination, calculating the sweetness of the resulting subarrays adds an extra layer of complexity proportional to the array's length. This means that the total time complexity becomes O n to the power of k asterisk n, which is extremely inefficient for large inputs. The impracticality of this approach for large values of n or k highlights the need for optimization. By combining binary search with a greedy approach, we can significantly improve efficiency. Instead of evaluating every possible split, binary search allows us to narrow down the range of possible minimum sweetness values, and the greedy validation ensures that a given value is feasible within the constraints. This drastically reduces the computational burden and makes the algorithm scalable to larger datasets. To implement the algorithm effectively, we rely on a few key data structures. First, the input sweetness array itself remains unchanged throughout the computation, serving as the basis for all calculations. Next, we use a generator or library function to produce combinations of k cut points efficiently, which is crucial for generating potential splits without unnecessary overhead. Additionally, we use variables to keep track of the maximum minimum sweetness encountered so far, ensuring we always have the best result available. These simple yet essential structures allow us to organize the computation systematically and focus on optimizing the approach rather than managing data flow. Let's illustrate the process with an example. Suppose the input array is sweetness equals 1, 2, 3, 4, 5, and k equals 2. This means we need to divide the array into 3 parts. We start by generating all possible splits, such as making cuts at indices 1, 3, or 2, 4. For each split, we calculate the sweetness of the resulting subarrays. For instance, with cuts at 1, 3, the subarrays are 1, 2, 3, and 4, 5. The sweetness values are 1, 5, and 9, respectively, so the minimum sweetness for this split is 1. We repeat this process for all splits, tracking the maximum of these minimum values. In this case, the optimal split yields a maximum minimum sweetness of 4, which is the result. This example demonstrates how the algorithm systematically evaluates splits to find the best possible outcome. Finally, let's analyze the complexity of the brute force approach. The time complexity is dominated by the need to generate all combinations of k cut points, which takes n to the power of k time. For each combination, calculating the sweetness of the resulting subarrays involves summing elements, which takes n time. Combining these, the overall time complexity becomes n to the power of k asterisk n. On the space side, we need to store the combinations, which requires k space, and we use a few variables for tracking results, which adds a constant space requirement. Therefore, the total space complexity is k. While this analysis highlights the inefficiency of the brute force method, it also underscores why optimizations like binary search and greedy algorithms are essential for solving the problem efficiently at scale. Here, we begin with the maximize sweetness function, which takes in the sweetness array and an integer k, representing the number of friends. The goal is to divide the chocolate into k plus 1 pieces with the maximum possible minimum sweetness. To break this down, we define a helper function canDivide. This function checks if it's possible to split the chocolate into at least k plus 1 pieces where every piece has a sweetness of at least min_sweet. Inside this function, we initialize current_sum n pieces to 0. As we iterate through the sweetness array, we accumulate the sweetness values in current_sum, and whenever it reaches or exceeds min_sweet, we count it as a valid piece and reset current_sum to 0. Finally, we return whether the total number of pieces is sufficient. Next, we define the binary search range for the minimum sweetness. The lower bound, left, is set to 1, since sweetness values are positive, and the upper bound, right, is calculated as the total sweetness divided by k plus 1. This ensures we consider the largest possible value for the smallest piece. We initialize result to 0 to store the maximum minimum sweetness found during the binary search. The while loop runs as long as left is less than or equal to right. Inside, we calculate the midpoint mid and use the canDivide function to determine if the current mid is valid. If it is, we update result to mid since we've found a potential solution. If mid is valid, meaning we can divide the chocolate with at least k plus 1 pieces at this sweetness level, we adjust our search range to look for higher values. This is done by setting left to mid plus 1, as we are aiming for a larger minimum sweetness. On the other hand, if mid is not valid, we reduce the search range by setting right to mid 1, indicating that we need to try smaller values for the minimum sweetness. Once the binary search completes, the result variable will store the maximum possible minimum sweetness that allows us to divide the chocolate into at least k plus 1 pieces. Finally, we return this result as the answer. This approach ensures efficiency by leveraging binary search over the possible sweetness values, and the helper function provides a quick way to validate each potential solution. Here, we begin with the Java implementation of the problem. First, we import the necessary utilities and define the solution class. Within this class, the main function maximizeSweetness is created, which takes in the sweetness array and the number k representing the desired number of friends. To help with the logic, we define a helper function called canDivide, which checks if it's possible to divide the chocolate into at least k plus 1 pieces, each having a minimum sweetness of min_sweet. The function operates by iterating through the sweetness array, accumulating the sweetness values into current sum. Whenever the accumulated sweetness meets or exceeds min sweet, we count it as a valid piece, reset current sum, and continue. Finally, the function returns true if the total pieces are at least k plus 1. After defining the helper function, we move on to setting up the binary search. The left variable represents the smallest possible sweetness, starting at 1, while right is initialized as the total sum of all sweetness values. To calculate this, we iterate through the array and add up all the elements, storing the result in right. Once we've calculated the total sweetness sum in right, we divide it by k plus 1, as this represents the maximum possible minimum sweetness for the pieces. Next, we initialize a variable result to store the best minimum sweetness found during the binary search. The binary search starts with a while loop that runs as long as left is less than or equal to right. Within the loop, we calculate the midpoint mid using left and right. This midpoint represents the current candidate for the minimum sweetness. We then call the canDivide helper function with mid. If it returns true, meaning the chocolate can indeed be divided into k plus 1 pieces with at least mid sweetness, we update result to mid and adjust left to mid plus 1 to explore higher sweetness values. Otherwise, if canDivide returns false, we adjust right to mid 1 to try smaller sweetness values. Once the loop ends, we return result, which holds the maximum minimum sweetness that satisfies the conditions. To solve this problem, we start with an example where the sweetness array is 1, 2, 3, 4, 5, and k equals 2. This means we need to divide the chocolate into k plus 1, or 3, parts such that the minimum sweetness of the pieces is as large as possible. We approach this using binary search. First, we initialize the range for possible minimum sweetness values. The lowest possible sweetness is 1, and the highest possible is the total sum of the array divided by the number of parts, which is 15 divided by 3, giving 5. We also initialize a result variable to store the best minimum sweetness we find. In the first iteration, we calculate the midpoint of the range, which is 3, and check if dividing the chocolate with a minimum sweetness of 3 is valid. Using the canDivide function, we add elements until the current sum reaches or exceeds 3, then make a piece and reset the sum. By the end, we can form 3 valid pieces. Since this is valid, we update the result to 3 and adjust the range to explore higher minimum sweetness values by setting left to mid plus 1, which is 4. In the second iteration, we calculate the new midpoint as 4 and check if we can divide the chocolate with a minimum sweetness of 4. Adding the first few elements, 1 and 2, gives a sum of 3, which is less than 4, so we keep going. Adding the next elements, 3 and 4, results in a sum of 7, which is greater than or equal to 4. This allows us to form one piece, reset the sum, and continue. Adding the remaining element, 5, results in only 2 pieces being formed, which is not enough to meet the requirement of 3 pieces. Therefore, dividing with a minimum sweetness of 4 is not valid, so we adjust our range by setting right to mid minus 1, which is 3. At this point, left is greater than right, so we exit the binary search and return the result, which is 3. Now, let's consider another example where the sweetness array is 5, 6, 7, 8, 9, and k equals 1. This means we need to divide the chocolate into 2 parts. Again, we use binary search to find the maximum possible minimum sweetness. The range starts with left at 1 and right at the total sum of the array divided by 2, which is 35 divided by 2, giving 17. We initialize result to 0. In the first iteration, we calculate the midpoint as 9 and check if dividing the chocolate with a minimum sweetness of 9 is valid. Adding the first 2 elements, 5 and 6, gives a sum of 11, which is greater than or equal to 9, so we make a piece, reset the sum, and continue. Adding the remaining elements, 7, 8, and 9, results in another valid piece. This gives us exactly 2 pieces, which meets the requirement. Since this is valid, we update the result to 9 and adjust the range to explore higher values, setting left to mid plus 1, which is 10. In the second iteration, the midpoint is calculated as 13. Checking with a minimum sweetness of 13, we add the first 2 elements, 5 and 6, resulting in a sum of 11, which is less than 13. We continue by adding the next elements, 7, 8, and 9, resulting in a sum of 24, which forms a valid piece. This gives us 2 valid pieces, so we update the result to 13 and adjust the range by setting left to 14. In the third iteration, the midpoint is 15. Adding the first three elements, 5, 6, and 7, results in a sum of 18, which is greater than or equal to 15, allowing us to form one piece. Adding the remaining elements, 8 and 9, forms another piece. This gives us two valid pieces, so we update the result to 15 and set left to 16 to continue exploring higher values. In the fourth iteration, the midpoint is 16. Adding the first three elements, 5, 6, and 7, results in a sum of 18, which forms a valid piece. Adding the remaining elements, 8 and 9, forms another valid piece. Since we can divide the chocolate into two pieces with a minimum sweetness of 16, we update the result to 16 and adjust left to 17. In the fifth and final iteration, the midpoint is 17. Adding the first three elements, 5, 6, and 7, gives a sum of 18, forming one piece. Adding the last two elements, 8 and 9, forms another valid piece. This is valid, so we update the result to 17 and adjust left to 18. At this point, left is greater than right, so we exit the binary search and return the result, which is 17. This problem demonstrates how binary search can be used to efficiently solve optimization problems by narrowing down the range of potential solutions. The CanDivide helper function is crucial for validating whether a given minimum sweetness value is feasible, ensuring that the solution respects the constraints. At each step, the algorithm balances minimizing and maximizing the sweetness by adjusting the left and right boundaries based on the validity of the midpoint. This approach guarantees that we find the maximum possible minimum sweetness for the required number of pieces. To analyze the time complexity of this solution, we consider the combination of binary search and the helper function, CanDivide. The binary search operates over a range defined by the sum of the sweetness array divided by the number of pieces, k plus 1. Let's break this down. The range of binary search is proportional to the sum of the sweetness array, which in turn is bounded by n times the maximum sweetness value in the array. The number of steps required by binary search is therefore logarithmic with respect to this range, simplifying to O log n asterisk max sweetness. Now, for each step of binary search, we need to call the CanDivide function. This helper function iterates through the entire sweetness array to check if it's possible to divide it into k plus 1 pieces with a given minimum sweetness. In the worst case, this takes n time per iteration. Since binary search requires multiple iterations, the overall time complexity becomes n asterisk log n asterisk max sweetness. Let's now focus on the space complexity of the solution. The binary search itself uses a few variables such as left, right, mid, and result. These are simple scalar values and require constant space, 1. The CanDivide helper function also operates with only a few variables, like current_sum to track the cumulative sweetness in pieces to count the number of divisions. These variables are also scalar and do not depend on the input size, so they contribute 1 to the space complexity. The input array, sweetness, is passed as part of the problem setup and doesn't count toward extra space usage. Hence, the overall space complexity of this algorithm is constant, or 1, making it very efficient in terms of memory usage. To understand the efficiency of this approach, let's compare it to a brute force solution. A naive method would involve generating all possible ways to divide the array into k plus 1 pieces and then calculating the minimum sweetness for each division. This approach would be computationally expensive, as the number of possible partitions grows exponentially with the size of the array. Specifically, it would take k plus 1 time to generate all partitions, and verifying each partition would add an additional n cost. This results in a total complexity of k plus 1, which is clearly infeasible for large inputs. In contrast, our binary search approach reduces the time complexity to n log n max sweetness, which is vastly more efficient. This optimization highlights the power of combining binary search with a greedy strategy. When analyzing the best, average, and worst cases, we see that the time complexity remains consistent across scenarios. In the best case, the binary search might converge to the optimal solution with fewer iterations. However, even in this case, each iteration of the binary search still requires processing the entire array via the CanDivide function, resulting in a complexity proportional to n log n max sweetness. For the average and worst cases, the binary search completes its full range of iterations, which involves O, log, n asterisk max, sweetness, steps, and each step requires O, n, processing. Thus, the time complexity remains O, n asterisk log, n asterisk max, sweetness, regardless of the scenario. To formally prove the big O complexity, we consider the two main components of the algorithm, binary search and the can-divide function. The binary search iterates over a range defined by O, log, n asterisk max, sweetness, as it narrows down the search space logarithmically. In each iteration, the can-divide function processes the entire sweetness array, taking O, n, time. Combining these, we multiply the time per iteration, O, n, by the number of iterations, O, log, n asterisk max, sweetness. This results in a total time complexity of O, n asterisk log, n asterisk max, sweetness. For space complexity, we observe that the algorithm only uses a fixed number of variables, without any additional data structures, leading to constant space usage, or O1. When solving this problem, there are some common mistakes that you should be aware of. First, incorrectly handling edge cases is a frequent issue. For example, if the number of pieces, k, is greater than the total number of chocolate blocks, or if k equals 0, the program can fail with runtime errors or produce incorrect results. The best way to fix this is by validating your input constraints and adding guard clauses to handle these edge cases explicitly. Another error is misinterpreting the problem statement. Many people mistakenly aim to maximize the total sweetness rather than maximizing the minimum sweetness. To avoid this, take the time to carefully read and fully understand the requirements before you start designing your solution. Additionally, some may attempt an inefficient brute force implementation, trying every possible way to split the chocolate. While this might work for small inputs, it becomes unfeasible for larger cases, often leading to time limit exceeded errors. Using optimized approaches, such as binary search or greedy algorithms, can help address this. Finally, skipping prefix sum optimization is a common pitfall. Recomputing the sum of subarrays repeatedly is inefficient and significantly increases computational cost. A more efficient approach is to precompute a prefix sum array, which allows you to perform range sum queries in constant time. Another common issue is off-by-one errors during binary search. Mishandling the low and high pointers can result in infinite loops or incorrect boundary conditions. To resolve this, double-check your exit conditions and ensure you're updating the pointers correctly. From an interview perspective, this problem offers several key insights. At its core, it often involves balancing competing objectives, such as maximizing a minimum value or minimizing a maximum value, which strongly suggests that binary search on the answer is the right approach. Problems that involve splitting arrays or partitions typically benefit from tools like prefix sums, binary search, or dynamic programming. Recognizing whether precomputations are necessary can make your solution more efficient. When discussing your solution in an interview, clarity is critical. If you propose binary search, be prepared to explain how you narrow down the search space and validate conditions. Interviewers are particularly interested in your ability to articulate your thought process. Additionally, you should be ready to discuss complexity trade-offs. For example, while a brute force approach may have an exponential time complexity, optimized methods like binary search bring it down to O, n asterisk log, max underscore sweetness. Emphasizing why scalability matters for large input constraints can demonstrate your understanding of algorithm design. This problem is also closely related to several other problems that use similar techniques. For example, LeetCode 410, split array largest sum, involves minimizing the largest sum among k subarrays. Another is LeetCode 875, Cocoa eating bananas, where the goal is to minimize the maximum eating speed. Similarly, LeetCode 1011, capacity to ship packages within D days, focuses on minimizing the maximum weight capacity. Lastly, LeetCode 1231, divide chocolate, requires maximizing the minimum sweetness when splitting chocolate. Recognizing these related problems can help you identify patterns and apply similar strategies. Now, let's discuss alternative approaches and their trade-offs. The brute force method, where you generate all possible splits and compute the minimum sweetness for each, guarantees a correct result. However, it quickly becomes computationally expensive, with a time complexity of O, n to the power of k, for k pieces, making it impractical for larger inputs. On the other hand, binary search on the answer is far more efficient. By searching over possible values of the minimum sweetness and validating splits using a greedy approach, you can achieve a time complexity of n*log max_sweetness. This method strikes a balance between efficiency and correctness, though it does require careful implementation of the binary search logic. Another approach to solving this problem is dynamic programming. With this method, you use a DP table to track the maximum minimum sweetness for different split configurations. This approach offers flexibility, making it easier to adapt to problem variations or additional constraints. However, it comes with its own trade-offs. Dynamic programming often requires more memory and can involve a higher implementation effort compared to binary search. While it may not always be the most efficient option, it's worth considering for scenarios where the problem's requirements align well with dynamic programming strengths. Great job making it to the end. In this session, we tackled the divide chocolate problem, reviewed key strategies, and highlighted important takeaways about optimization and problem solving. Remember to keep practicing and applying these techniques to similar challenges. Thanks for watching, and don't forget to like and subscribe for more content like this. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!